Good morning, all of you. Our today's topic is again a refraction, a particular important topic. Let's consider two medium N1 and N2. Light travels from N2, second medium, to N1. For example, if this is denser medium, N2 is denser medium, like water or glass, and N1 is rarer medium, light goes away from the normal. This you can see, this line is bent a little bit towards the right side, that is away from the normal. So this is angle of incidence and this is angle of refraction. So this is a typical case of refraction in which light travels from denser to rarer medium. Now what happens to this angle of incidence? If I is the angle of incidence, corresponding angle of refraction is R here. We have the relation that is Snell's law, sin I by sin R is N2 by N1. So in this case, if we apply sin I by sin R will become N1 by N2. Sin I by sin R is refractive index of second medium. This is the second medium here, by the refractive index of first medium. Now if you increase this angle of incidence, if light comes at a greater angle, if it comes at a greater angle like this, here you can see this angle I is greater than this angle I. So in that case what happens is light bend more. So here light bend more and the angle of refraction also increases. There is a particular case in which for a special angle of incidence, this angle of refraction increases and becomes a 90 degree, like this. If angle of incidence, for a special angle of incidence, angle of refraction becomes a 90 degree. This angle is called a critical angle, and that depends on refractive index of the two media. Now if any light falls at an angle greater than this critical angle of refraction again increases, and further increases means light comes to the same medium, like this. So here angle of refraction is again increased, it is more than this 90 degree, it comes back to the same medium. That means now this light has got completely reflected back. So here all light was refracted, this case light was refracted. Of course there will be some little bit of reflection in all case of refraction. For example, when you stand in front of a pool nearby a tree, you can see the reflection of the tree on the water surface. At the same time you can see what is inside the pool also. If the water is still, you can see what is inside the water, that is through refraction, and the reflection also you can see. So in all cases of refraction there is a reflection also, but if light falls at an angle greater than critical angle, for critical angle of refraction will be 90 degree, but for an angle greater than IC critical angle of refraction is again increased. In effect it gets reflected, completely reflected back. This phenomenon is called total internal reflection. So for total internal reflection to happen, light should travel from denser to be rarer medium, and the angle of incidence should be greater than critical angle. And now let us check what is the value of this critical angle for a given pair of media. For example, let's consider light travels from water to air. That is, the denser medium is water and the rarer medium is air. So if you apply Snell's law, that is sin I by sin R is equal to refractive index of second media divided by the refractive index of first medium, we get a refractive index of second medium as Na, because second medium is air, and the refractive index of first medium is water, Nw. Refractive index of air is Na and the refractive index of water is Nw. We know that the refractive index of air is 1, and for a particular angle, that is IC, critical angle, when I is equal to IC, angle of refraction is 90 degree. We have seen just now. So we substitute I equal to IC and R is equal to 90 degree. So sin 90 is 1. So we got a sin IC is equal to 1 by refractive index of water. So this is a general case. Whenever light comes from any particular medium, any denser medium to air, sin IC is 1 by n, where n is the refractive index of that particular denser medium. So if it is water, sin IC is 1 by n water. So for example, if light goes from glass to air, if it goes from glass to air, n is 1.5. So from here I can substitute. Here I have sin IC is equal to 1 by n, that is n is equal to 1 by sin IC. N equal to 1 by sin IC. So 1.5 is equal to 1 by sin IC. From this I can find that angle as nearly 42 degree. So just replace the angle, replace the refractive index of that particular medium. If it is water, you can substitute it as 1.33. If it is glass, let n be 1.5. So for an angle 42 degree, we get critical angle. That means whenever light try to come out of glass to air, if the angle of incidence is greater than 42 degree, it gets reflected back inside the same glass, and this is called total internal reflection, and it has many applications. For example, our optical fibers are working under this total internal reflection, and on very hot sunny days, you can see on the road, if you travel by car, on the road you can see some mirage. That is also with the help of total internal reflection. So you can refer page number 320 to 323 for getting applications of total internal reflection. Let us consider another one topic, that is refraction through prism. So already we have seen refraction through glass slab. Now we have a refraction through prism. So for that we can consider a prism. You have already seen a prism. It is made of a transparent material like a glass, and it has a 2 triangular surface and 3 rectangular surfaces. Like this side is a triangle, this side is triangle, the 2 triangular surfaces, and 1, 2, and the bottom 3 rectangular surface. Every prism has an angle. The angle of prism is marked as A, and usually this will be an equilateral triangle, so this angle will be 60 degree. Almost all prisms, the angle of the prism will be 60 degree. So here A, B, C, E, D, F, these 2 are the triangular surfaces, and A, B, E, D, this is one rectangular surface. AC, FT, this is also one rectangular surface. BEFC is another rectangular surface. So we call this as some names. BEFC is the base of the prism, where you keep the prism. This is the base of the prism. BEFC, this surface is the base of the prism, and this surface ACFT and ABED, these are refracting surfaces. through that light will get refracted. So when a monochromatic light means a particular light with a single wavelength, just a particular color like a red color or blue color light is incident on any refracting surface like A, B, E, D or A, C, F, D. Like when it undergoes a refraction from here to here, that is from air to this glass, when it enters, it bends towards the normal, but finally when it comes out of this glass from this surface outside, it bends away from the normal, like a denser to rarer and rarer to denser. So some mathematical part we will see regarding this. Now we consider the triangular side of the prism. That means ABC only we consider. This is the angle of the prism A. Let a light ray comes, light ray is PQ, incident light ray. It falls on the prism and here is the normal at this surface AB. So for this surface AB, this is a normal. This light ray PQ makes an angle I with the normal, and if there is no refraction happens, this light PQ should go and it should reach up to P dash. This is the direction in which PQ should go without any deviation, but we know there is a medium change, so light will get refracted. So here, as I said, A is the angle of the prism, BC is the base is BC, and PQ is the incident ray. Now this undergo one refraction, that is like this it will bend. QR is the refracted ray inside the prism. QR is the refracted ray inside the prism. Now this is the normal here. This is the normal, extended normal. As light travels from air to glass, it bends towards the normal. This is the normal, so it should bend towards the normal. That's why this QR is marked here. Now finally, light enters from glass to air. Again, that bend away from the normal. So here also we can imagine a normal. This is the normal. So at this point, light goes away from the normal, and RS is the final emergent ray or emerging ray. So three rays: incident ray, refracted ray and emerging ray. Two normal, one here and one here. This is the original path without a deviation. Now let's consider the angle of refraction. So here is I as angle of incidence, and this is the refracted ray making an angle of refraction R1 with the normal. So the first angle of refraction is R1. So here we have two refractions happening. So two set of angle of incidence and refraction will be there. So first angle of incidence is I, corresponding angle of refraction is R1, and here you can mark the remaining angle. So if this line, if we consider, this remaining angle will be this remaining angle will be I minus R1. So we have considered this alone, angle of incidence I, angle of refraction R1, this remaining angle I minus R1. Now this is our refracted ray, but here for this surface alone, for this part alone, this is our incident ray, this is our refracted ray. So here is a normal. This angle of refraction we mark as E, and that we call as angle of emergence. Now this is the actual angle of incidence here. We will mark it as R2. This is R2. This angle is R2, and this is full is E. This alone is R2. So this remaining will be E minus R2, because you see this dotted line and this line. Here is a dotted line. This line make equal angle. This E is equal to this full angle from here to here. So if this is R2, this is E minus R2. Now this is the actual path of the light. QP dash is the actual path of the light. But now the light has reached a path RS. It is taking a path RS. If you extend this, you get a point here M, and this is the angle delta through which the light has deviated from its original path. This is the angle at which the light has deviated from its original path. This angle is called angle of deviation, and that is marked as delta. And our intention is to find what will be the angle of deviation delta, what will be the value of delta in terms of refractive index of the prism and the angle of the prism. So for that we'll go with some mathematics. So first we can take some of the angles here. Look at triangle QMR. Let's consider triangle QMR. This triangle. This is I minus R1, this is E minus R2. If I add I minus R1, E minus R2 and this angle M, I should get 180 because it's a triangle. So which means angle M is 180 minus this plus this. So if I write like this, I get angle M is equal to 180 minus I minus R1 plus E minus R2. I minus R1 plus E minus R2. I minus R1 plus E minus R2. And also look at this. This is a straight line. This is a straight line. So this angle delta plus this angle M, if I add, I should get 180 because angle made at a line is 180 degree. Angle M plus angle delta should be 180. That's what I've written here. Angle M plus angle delta is 180, so which means angle delta, the deviation is 180 minus angle M. But angle M we got just now 180 minus I minus R1 plus E minus R2. Substituting this 180 minus this angle 180 minus I minus R1 plus E minus R2, we get it as I minus R1 plus E minus R2, which means in simple, if you are good in mathematics, we get this angle and this two angles sum are equal. Directly I can say like that, but if you have confusion, go in this way. So this angle delta should be equal to sum of these two angles. So that is what written here. Delta is equal to I minus R1 plus E minus R2. I plus E I write together, then R1 and R2 here. Look at this QARN. QARN. If I add A and N, angles A and N, I should get 180 degree. That is sure. That is, see the first equation. This equation is E. Angle A plus angle QNR should be 180 degree. Let us check what is that angle N or angle QNR. So this plus this is 180. Now we will check what is this angle QNR. Here is R1 and R2. You know R1 plus R2 plus N is 180, which means N is 180 minus R1 plus R2. R1 plus R2 plus N is 180, which means N is 180 minus R1 plus R2. So that is written here. angle A plus angle N is 180 minus R1 plus R2, that is equal to 180 degree, which means angle A is equal to R1 plus R2. 180 by 180 cancel, which means angle A will be equal to, so from this we get angle A is equal to R1 plus R2. Now we go back to the equation. We had consider this angle, delta is I plus E minus R1 plus R2. Now we got R1 plus R2 is equal to A, so delta is equal to I plus E minus A. So this is the case. Angle of deviation is I, angle of incidence plus angle of emergence minus angle of the prism. Now after doing a lot of experiments, after experimental study, it is seen that as I increases, angle of incidence increases, angle of deviation decreases. It's an experimental fact. As I increases, angle of deviation delta decreases. Initially, it happens initially, and it reaches this angle of deviation becomes a minimum value, and again that increases. That is, if you show it as a graph, angle of deviation and angle of incidence, if you plot, angle of deviation decreases as angle of incidence increases. Initially, as angle of incidence I increases, angle of deviation decreases for a maximum value. After that, it again increases. So this particular minimum value of angle of deviation, it is seen that this happens when I is equal to E. Through experiments, it is seen that this angle of deviation becomes a minimum when I is equal to E. When I is equal to E, look at this picture again. When I is equal to E, this will become a straight line parallel to BC. QR, refracted ray, will be parallel to the base BC. In that case, R1 and R2 will be equal. Let us take that R1 and R2 is equal to R, and already we have R1 plus R2 is equal to A is equal to R1 plus R2, which means if R1 and R2 is taken as R, then we get R is equal to A by 2. And one more thing we told, at this case when I is equal to E, angle of deviation is a minimum from the graph. Delta minimum is equal to I plus E is again I itself. So 2I minus A is angle of minimum. 2I minus A is angle of minimum, which will give you 2I equal to delta minimum plus A, or I is equal to delta minimum plus A by 2. This is what written here, angle of incidence. For this case, I can write angle of incidence is equal to delta minimum plus A by 2. Now let us apply Snell's law. Snell's law says sin I by sin R is equal to refractive index of second medium with respect to air. Here second medium is glass, so first medium is air. Sin I by sin R is equal to NGA. This is actually NG by NA, but we know NA is 1, so NG itself it will come. Just now we got I is equal to A plus delta M by 2, delta A plus delta minimum by 2, and we got R also. We got a 2R is equal to R plus R is equal to A, or 2R is equal to A, or R is equal to A by 2. So that also, if you substitute, sin of A plus delta by 2 is equal to divided by sin A by 2 is equal to N glass. So this relation gives the refractive index of the prism in terms of angle of prism and the angle of minimum deviation. So if you know the angle of the prism and angle of minimum deviation, we can find the refractive index of glass. We have a special case here, just for a special case. For thin prisms, very thin prisms, we can consider these angles are very small. All the angles will be very small. So in that case, sine theta is nearly theta. For small angles, sine theta is nearly theta, which means sine of a plus delta minimum by 2 can be written as just as a plus delta minimum by 2. And sine a by 2 we can write as a by 2. So refractive index n, which was sine a plus d by 2 by sine a by 2, we can write sine of, instead of sine we can write the angles itself a plus delta minimum by 2 by a by 2. If you do that, we get another equation, that is delta is a into n minus 1. So this is applicable for very thin prisms. For angles are very small. But the generalized equation is this itself. This is the general equation for the refractive index of the prism.